So home stretch. You get to go have lunch after this. I want to spend just a little bit of time talking about who this message is for. It's for everybody in the room. There's some messaging here if you're trying to figure out what this is all about and you're not an engineer. There's some messaging here for open source development community. And there's some announcements here about how serious Rackspace is about seeing this become a core part of open source software development for the future. We call that soft hardware. I want to talk a little bit about our journey so far. So last year, we showed a slide very much like this, and we said we're on a journey here to get a server up running Power at Rackspace. And then, once all of those bits are done and that server's open from top to bottom, we're going to put it on our public cloud, basic OpenStack orchestration. And then we're going to go to work on accelerators and CAPI, like what you see here. So if you look at the map here, we're just past basic cloud orchestration. And that looks like about halfway done, but I'd say we're more like a third of the way done. The most interesting parts come next. Ultimately, what we want is for our industry to get to a point where software developers think about acceleration as naturally as they think about any other type of software development that they do today. And that's a big change from where our industry is right now. So these are pictures of our server. We have a green board up on the table here. When we took these photographs, they're blue board. That's Barrel-I in a rack on your right, I guess your left, and that's with the lid off on the other side. And that's a photograph of the motherboard itself with the I/O board in the front. We've put samples of this server out, working with IBM to many other partners. I think if you look at the material we have for PR here, that there are a number of other parties that are taking this to market, and we're pleased to see that happen. These are some of the key partners that we had in this development effort, and we'd like to thank every single one of them. They put a lot of time and effort in. A year ago, we stood up with a board that didn't have any wires in it, and now we're shipping. Everybody loves green boards. Now we're shipping to our data center. We just started shipping, and we hope to be in production with this with customers online in a few months. So we think of this as the starting point to get into things like CAPI and NVLink. Okay? This is a server that represents not just something we can get production value out of on our cloud today, but it's a sandbox of sorts, and we'll come back to that in a minute. We also want to announce that we are working on Xayas with Google. Of course, you heard that already. These are just some pictures, some photo renders of the board and the specifications that we have in place. And this is actively moving forward right now. Xayas' motherboard is a little bit smaller than Barrel-I's motherboard, so it should fit in more form factors than we have today. But the image you see here is a Barrel-I-like form factor that we've modified just a little bit to take advantage of some of the extra capabilities in Power 9 and to work with 48-volt power distribution. And that's a rendering of the front of the system. We did also develop an option where you can run it without disks for applications that want to save a little bit on cost and power there. So why do we do this? Why spend all this effort? If you're in the room and you're wondering what is this really all about, why is there so much noise, why are so many systems here, everything looks pretty well fine. You know, Moore's Law doesn't seem dead to me. Let's talk about that in a way that's really easy. We're kind of in a valley right now when it comes to getting more performance out of our systems, and our demands are going up. The size of our data sets are going up. The responsiveness that we want in all of these different applications, from cab rides to genomics, the demand just keeps going up. So software is eating the world, and it's been a gold mine for all of us. Unfortunately, because of this Moore's Law problem, we are biting into very hard parts now. And we got to work together to solve this problem. And most of us that are dealing with this performance problem over the last few years, trying to figure out how to get around it, without something like OpenPOWER, it feels a lot like this, including the temper tantrums and the pain. Okay, I think at this point we have all moved, though, from denial to acceptance. And you've heard a little bit of this before. You can tell that as a community, we're all aligned when we stand up with our own individual presentations, which we did not coordinate on in advance, and tell you the same thing over and over again. We're all thinking the same way. Okay, here's the first one. Intel talking to MIT Technology Review. Just a snippet of that. You can find that in the last couple of months. Right? We found a new material, but the material, while giving us much lower power consumption, will also be slower. And that's great for mobile. That's kind of scary if you're in enterprise or hyperscale computing. Most of our tasks need strong performance and continued growth there. And then Nature. So all the people that publish in general scientific journals understand this. And finally, my favorite one, Ars Technica. We're going to get into a little more here. They wrote an article. They're more for the hackers and the enthusiasts. And Moore's law is dead after an extended illness. And in the future, we're going to have to break laws. That's going to become normal, breaking laws in how we write software and design systems. So just to put a little humor on it, physics is Muhammad Ali, and we're on the mat right now. We have to design different software and hardware. So if the tech elements there, if the news media there doesn't hit you, you're more the economist type. This is sort of how we've gotten improvements in our cost of capacity over the last few years. We optimized our data centers, we optimized our supply chains, we got better components, we improved our code. You'll see something about that soft hardware in a minute. And for most of us, this is a hypothetical provider in hyperscale services, but for most of us, we sort of got our TCO improvements, our cost of capacity improvements, by a cumulative effort across these things. But as time goes on, it's really hard to squeeze a data center from 1.01 PUE down to 1. That's a lot of work. You get 1% out of it. You can only squeeze your supply chain so hard. You can only do other things. And these things get more and more costly, just like us trying to master the next material for CPUs and memory. You get diminished returns. And so over time, our investment, the size and scale of our investment increases, and our return gets smaller. If you're in this industry, the average of this, even if it's not exactly this line, is probably your line unless you're doing acceleration. And cumulatively, industries do better when they're on the steep side of that curve. Cumulatively, we're flattening as well. Okay? Industry grows really fast, and we all feel wealthier and better when we're on the steep side of this curve, not the flat side. Okay? We don't want this to be our line going forward. Consumers won't tolerate it. So what if instead of that, you could think about a future where the line, even though we're making little improvements, looks like this. Now, it's fun. You can play with this in a spreadsheet and put whatever number in you want. But this is a real application in this case that we modeled this on. And now we want to do this with more than one. We want to do this with almost every application that we have, so that our cumulative line can look more like that. So what makes that possible? There's been a lot of talk about it. The next little bit, I'm going to try and demystify this a little bit. It's still technical, but we've used some video animation and some other things to help you understand what makes this possible. The important thing I want you to understand with this picture is that steep curves like that require steep climbs for our industry. And some of that's been going on already. Okay? I want you to think about the fact that we've got a system, and that system works really well, but we need to reintegrate the system and how it works. You've heard Brad talk about new kinds of memory. You heard Jeff talk about new interfaces in the systems. That law breaking that we're referencing is really, it's breaking the de facto rules on how systems ought to be designed and on where code ought to run and where data ought to be stored. We've had common rules there for a long time that have worked for us, and we didn't change them because we didn't need to. When you change some of those rules, things get harder for all of the code and all of the people that write on top of them. Okay? So that's a challenge, but we have to do it in order to hit that economic benefit. So think about a factory for a minute, and think about when you invest in a factory, you want the maximum amount of throughput. And if the factory doesn't give you the maximum amount of throughput, what you do is you retool it. Sometimes you change the production line a little bit. Sometimes you change the interactions between the lines. But whatever you do, you're always looking for ways to maximize that investment. So let's talk about the system like it's a factory. Here's your front door. And you step into your data center, and you got a rack. And you got production lines in those servers. Some of those racks are production lines in and of themselves. Okay, you've got applications that are production lines. And with Linux and OpenStack and OpenCompute and many other open source projects, we have managed to optimize at this layer. But there are more production lines inside these systems. Okay, so this is just a prototypical server. It's got memory, it's got a CPU, and it's got some sort of I/O device. Now, it's going to take you a minute to ingest this, so just give yourself a moment while we watch. Up at the top, you have a set of sequences for your application to complete its work. What kind of things is it doing? And there's a little red ball that you're going to see moving around. It's basically like sort of the critical element in the path. What's being talked to, and how much time is it taking? And down on the bottom, you can see how many cycles are getting spent and how many microseconds it takes to serve things. And I know microseconds are really small things, but in computer world, too many microseconds is kind of like eternity for the rest of us. Right? And all our servers do when they're running all these apps is today, they just bounce this data, this code, this basic process back and forth through the system. And it takes a lot of steps. That transaction took over 130,000 cycles and quite a few microseconds. So if we can't make the buses go any faster, the processors go any faster, and the cards go any faster, what we can do is take the overhead out. So here's that same scenario over again, but now we're doing accelerated co-processing with something like CAPI or NVLink. Okay, on the side to your left, you have the same video I just played you, and on the side to your right, you have an accelerated system. But we've slowed it down so you can actually see that ball moving around. Okay? The one on the other side is slow motion, and you see the word cohere a lot. That's our word for everything in the system behaves like memory and processors now. It's not all just I/O anymore. You can kind of imagine a world where we can just kind of make the system work how we want it. We just need to make sure it's stable. And if you play that back at full speed, again, a simulated transaction on a real system. Okay, take a look for a minute. Now we're running that video at full speed, and you can't even follow the ball anymore. And by the time one transaction's done on the other system, 10 transactions have been done on the reintegrated system. And this is not magic. There's already benchmarks out there showing this. There's already proof points in the industry, but there's only a few proof points. And this is not the only use case that you can do this with. If you want to change how your memory interface works today with CAPI, even without the memory buses that Jeff talked about, you can kind of make your own with these cards. You can make them out of NAND or anything else. So we play the video here. It's a little bit slower because on the one side we put expensive NAND, and on the other side we put cheap NAND, and NAND is what helps it scale. But this particular simulation runs 2.5 times faster on an accelerated interface than it does on a standard one. And as NAND or whatever memory we use gets faster, the order of magnitude of that change will increase considerably. The improvement will go up considerably. And we've been messaging this for a long time, but I would love it if this was the year when our peers and the people we talk to that are skeptical about this and unsure start really honing in on this message. Okay? Start taking this very seriously. This is not just for a couple of applications. It's not for a limited subset of things. It's for all kinds of things. Today, 3-tier web applications are really popular. You have your web servers and your cache and your database all on separate systems. What if part of your savings comes from just collapsing that web tier and that cache down into a card that lives on your server, and then you tightly integrate it with your database? Your server count goes down, your latency goes down, your power costs go down, and your performance goes up. And that's just one other example. Many, many ways that this can be fit. As I said earlier, because it's bending the universe of how we design systems, you're also dealing with a problem where not too many software developers know what to do with this and know how to deal with these changes in the rules. So how does it happen? How do we get software developers to a point where all of them can start to participate in this? And how's that going to happen? The first thing I want you to think about is that it already is happening. And at a Power Summit, it's odd to have a Microsoft slide up here, but a couple of years ago, Microsoft published a paper, and they went into a lot of good detail about how they're doing it for their search engine. And that is a standard Microsoft Open Compute form factor system. And they tell people that want acceleration, something the CPUs can't do, hey, just put one of those cards in it. We've got a tool chain and a code base that you can begin to use to get acceleration on your service. And they call that Catapult. When they wrote a research paper on there, when they finished, I took a couple of extracts that I thought were the most interesting. And this is true for all of us here. Okay? We need to start thinking about compiling to a combination of hardware types and software. The data centers are going to change so fast and the applications are going to change so fast that if we don't have programmable, what we call soft hardware, it's going to be impractical to keep up with the pace of change because you can't tape out fixed function chips fast enough to keep up with the changes. So you need more types of chips, more flexible chips. Finally, how is it going to happen? So they said, hey, we did this, but it was a lot of very specialized developers. It's difficult to program in this space today, and if we want to move it beyond specialists to the masses, we need better tools and more code. And so here we could think about Barrel-I and what we're doing here, and with Zaius, what we're doing with Google, as a hyperscale grade open source sandbox. No licensing inhibiting you from going where you need to go and how you want to learn. No fears about your IP running on top of that server if you're doing it in open source. And you put a developer-friendly accelerator platform underneath it, and then we give it to as many people as we can so that they can start experimenting. Okay, and that's a start. Now, there's also the tools. Okay, how are we going to build this stack? Well, first of all, today, developers are not really where we need them. We've done this to ourselves in the industry with things like Java and Python, but if you think about developer demographics in this stack, we go all the way down to the digital logic. And today, most of our developers live in the world of scripting and very abstract languages. So Mara mentioned that Google has developed tools to make it easy for developers to adapt their applications. And I think some of that sort of is going to require us as an industry for the broader set of applications to sort of shift where people live and develop. Now, I don't have any like percentages here. We really just put little guys next to each other typing to what felt like the right proportion on the image, but you can see there's a shift. Hey, now, here's the other challenge. Today, in the cloudy world, we do not have what I would call a traditional educated, brought-up hardware developer as our mainstream target. Okay? We have those sorts of people. They don't scale. Okay? That's computer engineering programs at universities. That's years of waiting for them to get experience in the companies they do this with today. And we don't have many traditional software developers left that work way down the stack unless they're writing operating systems or drivers. We have very clever developers, and we love what they do because they make our life more convenient and more interesting. And those entrepreneurs are Python developers. We showed this last year. So what if your world mostly consists of this sort and you want to retool? Because the big challenge here is their lab where they learn things. It's not a white space with servers with probes hanging out of it and things like that. It's a laptop in a Starbucks. And these things don't fit on a Starbucks table very well. Well, you can start by just getting hardware out there in the hands of developers. There's two guys in the room that might be feeling a little embarrassed right now looking at this picture. We got them some Cappy cards a few months ago. One of them has background writing OpenStack cloud code for us and working on one of our platform as a service products at Rackspace. And the other one came from the world of embedded development. One just sort of an enthusiast on these things, another one a little bit more experience. Okay? And our first task was go to work doing this reintegrated sort of NAND as memory system. And I started asking, hey, how long do you think it will take you to write this if you just do it yourselves? And I didn't say anything. I just watched. Right? And over time, like they're making progress. They're having phone calls with our partners in OpenPOWER. It's pretty fun to watch. But then we sort of got to the point where I said, do you realize in order to do this, that's the Linux storage system stack. You have to kind of refactor that whole thing, and you have to do it in a new language on a new kind of chip. in a new kind of hardware for us. This is hard. Okay, on the one hand of your screen in this development environment, you have what looks like normal computer code. On the other hand, you have digital logic. How many Python developers even know what digital logic is? I work at a company that has a lot of them, and the answer is precisely 0.012% or something like that. Okay, so I presented with some challenges here, but the important thing to remember is as we make progress here as a community, this is how we get to 10x. So this is not a question about whether or not it's going to happen. It's a question about where it's going to happen and how it's going to happen. Is it going to be available to everybody? Is it going to be concentrated in just a few places? Is it going to be open or proprietary? If I were working at a company that liked the proprietary route, I'd be licking my chops right now, because if I can deliver you 10x, even if it's closed and you don't like closed, you're going to buy it because you have to compete. You're going to resent it the whole time, but you have to compete. And this is important. This is why open source and OpenPOWER matter so much. So the next question is, all right, how do we compete? How do we get there faster? Okay, as we get starry-eyed for a minute, I want you to remember just a couple of things. First, make sure everything you're doing in this space, if you're participating, is open. You don't have to open here, but you should. Make sure it's easy to access, and make sure you've done what you can with documentation and otherwise to make it developer-friendly. It is extra effort on your part, but we start a momentum going. We start a flywheel going that gets going faster and faster and starts looking like what Linux and OpenStack is today, which is really fast and really productive. The next thing, you've got a lot of hackers that are interested in this. If you want to enable them, you have to open source it, like I said before. You have to take what you did and give some of it away, because they learn by experimenting with what you already did. And that's how some of our people are learning right now. Finally, ask just for a minute, in all the applications we could work on, for those that are out there and hacking on this, what types of applications bring value to me that also really excite and motivate other developers? So it's not just a cool story, it's something that they want to go work on too, because it's going to make their lives better. Pick those projects first where you can. Okay. The nexus of all of this, open source software, open source hardware, and open chip technology, is where our big speed ups come from. It's where soft hardware lives. So this is a multi-community effort. Again, that's partly why we're doing this with Open Compute and an OpenPOWER. Okay. Just for a moment. Everybody loves space shuttle stories. You want to get to the moon? You got to bring a lot of people from different disciplines together. You give them a big, crazy challenge. You tell them how awesome it would be if we got there. Okay? And it's not just the shuttle you build. You got to build the platform underneath it as well. And it's a broad, broad effort. So think about the story of NASA in this case. All those people together and fairly democratized. If you can contribute, we'll take you to help build this thing. And then think about staring back from the moon back to Earth for a minute. Okay. Some of us sort of talk and smile about things like punch cards. Some of us smile about the client-server era before there was clouds. Okay. When we do this and it's done, we will look back on this era that we're just coming out of as something that was kind of quaint. It was cute. I remember when we were there. Do you remember how limiting all the technology was at that point? I mean, it was the best thing we had at the time, but it was, it was kind of limited. Think about that for a minute and all the potential that we're going to untap. And then remember this, please. Our mission over the next couple of years as a community here is to make sure that that shuttle and launch platform that takes us to the moon and takes us to 10x stays open. Please insist on it. Okay? If you do that, you will make life better for all of us and we will all benefit. Thank you.
Wow, okay, thank you. Thank you, our presenters, that was awesome. A round of applause again for all the presenters. Wow, wow. I'm just getting chills thinking about it. Okay, so hopefully you enjoyed the morning. There was a lot of material presented. I hope you are with us for what comes next for next year. Okay, so quick logistics. Press, please come up and take your pictures. We'll be moving this stuff out to the pavilion, so in the afternoon you can come look at it in more detail there. For the rest of the audience, IBM actually is doing a keynote about Watson, which is going to be very interesting. It's starting like now, so if you go out and make a right, you can join us there, and we'll see you all back here at 1:30. Thank you very much. Oh, yes.
One announcement, guys. So for everyone, the hardware kit will be available here through 11:30 for you guys to view it. At 11:30, we'll be moving it to the pavilion floor. For those that are technology providers providing these systems, we ask you to please be at the pavilion floor at 12:30. We're going to take a shot encompassing everybody behind the boards, what we call the money shot. So please be there at 12:30. The money shot. All right, thanks, guys.
That way, but okay. Thank you. See you 1:30.